Good morning. Last time we talked about confidence intervals in the context of a mean. This gave us a way to come up with a best guess for the true population mean. In this section, we're going to look at a confidence interval for a proportion. So what do I mean by a proportion? As an example, let's say we want to find a 95% confidence interval for the true proportion of Americans who love lima beans. Probably pretty low. So that proportion could be 0.8, could be 0.9, or we could even describe it as a percent. 80% of Americans love lima beans, or 90% of Americans love lima beans. So in this section, we're looking at a proportion. We're looking at a situation where we have two possible outcomes, success or failure. So the Bernoulli distribution, or the binomial distribution, should come to mind. So let's list out then the assumptions that we're going to make for this section, and then we can develop our confidence interval. So my assumptions are that I have, as I said, two possible outcomes. So you have success or failure. And again, you can arbitrarily define which one is success, which one is failure. Second, the outcomes are independent. If you know that one person likes a lima bean, it's not going to affect whether the next person loves lima beans. Third, P and Q, these guys are going to be our parameters. We only use Q very briefly. Q is just 1 minus P. So this is Q is our true probability of, or proportion of failure. That's our true proportion of success. We're going to use P hat and Q hat to represent our statistics. These guys are coming from the sample. So for example here, let's say you polled 100 people. This could be something like 60 out of 100 might be your P hat. So with this in mind, the assumptions that I want to talk about are that NP hat and NQ hat should be greater or equal to 5. So this is similar to the N is bigger than 30 in the mean situation. This makes things normal, more or less. And again, this is less theoretical, more by experience. That's how I would like to think about it. Okay, so this is the situation we have. So let's start diving in to find the confidence interval using an example. And the good news is that the process is pretty much the same as what we did in the last section. Let's do an actual example. For example, say I flip a coin 10,000 times, and I obtain 4,900 heads, and I'm going to call this a success in this context, and 5,100 tails. So the question that I'd like to ask is, do you think the coin is fair? So first off, if I got 5,000 heads and 5,000 tails, hopefully nobody would have a problem and say, oh yeah, of course it's fair, right? It's 50-50 chance and I got 50-50. As I stray from 5,000 on either side, I'm less inclined to think that the coin is fair. As an example, if I got 0 heads and 10,000 tails, I would most definitely not think that it is fair. I'd like to come up with a process by which I can kind of quantify this statement so it's not just my gut feeling, but I have some numbers to back it up. So this is what I'm going to do. I'm going to compute a 95% confidence interval. I'm going to compute a 95% confidence interval for heads. If my interval that I come up with using the process that we're going to develop, if that interval has 0.5 in it, so for example, let's say it turns out that I get 0.47 to 0.51 after I figure out how to do this. Well, if I get this, then this is telling me that I'm 95% confident that this interval captures the true proportion of heads. And in that case, yeah, I have no reason not to think that the coin's fair. Why? Because 0.5 is in that interval. If on the other hand, I compute this and I get 0.491 on the high side, 0.489 on the low side for my 95% confidence interval, well, then I don't think this coin is fair because, again, this would have been derived from a process by which 95 out of 100 times I would capture the true proportion. I'm looking at this one and, well, it's not capturing the true proportion. It's not capturing 0.5, so I don't think it's fair. Now, this isn't proof that this is fair or not. That's the thing about statistics. That's the trade-off you have. You're never going to actually know, but this is evidence in one direction. So how are we going to do this? Well, there's going to be a little bit of hand-waving going on in this section, but hopefully it'll seem like reasonable hand-waving. So the first bit of hand-waving that I want to say is that p hat, so p hat, again, was the sample probability of success. P hat is normally distributed. So why does that seem reasonable? Well, oh, and actually even better than normally distributed, in fact, p hat is normally distributed with true proportion, with the mean being the true proportion of success. So why does that seem reasonable? Well, let's say the true proportion of success for something is 0.6. So 60% of Americans really believe blah. And you go out there and you talk to a sample of 100 Americans, and you find that in that sample, 62 of them support blah. So that's 0.62. Well, if you do that again and again and again and again and again and again, if the true proportion is 0.6, if the true proportion happens to be 0.6, then I would expect most of my samples to be around 0.6 because that is the true proportion. In addition, as I go higher than 0.6 or lower than 0.6, I would expect fewer and fewer samples to look like that. Once again, this is the normal distribution picture. So that's not a proof. That's the hand waving, but hopefully you can buy into that. Because if you buy into that, guess what? The 95% confidence interval proof is exactly the same as what we did for the mean. Why? Because once again, we have a value p hats of 0.025 out here. We have a value minus p hats of 0.025 down here. We have 0.025 here. We have 0.025 here. I call this E, same game. So my claim is that p hat plus or minus E is my 95% confidence interval. So pause the video, see if you could reproduce the visual proof that we did with the mean. All right, hopefully you did that two-finger proof, the most sophisticated proof that you'll ever do. Let's say this happens to be p hats of 1. I'll take my two fingers, move it this way, take my two fingers, move it that way. That time I captured the true proportion. Let me do it again. Let's say p hats of 2 happens to be out here. Take my two fingers, Take my two fingers. That time we didn't capture the true proportion. Well, 95% of the probability lives right in here. And the only way for me to capture the true proportion by this process is if my p hat happens to be between here and here. Happens 95% of the time. So once again, we need to now come up with what E is, now that we believe that this is the correct form. So let's try to come up with E, and once again, the central limit theorem is going to come to our aid. So Z sub 0.025 is going to be P hat minus, P hat's of 0.025 minus P over the square root of PQ over N. So pause the video, see if you can figure out where's this stuff coming from. Well, hopefully you said, oh, this is just going to be a Bernoulli distribution because each person is either going to be a success or a failure. Well, that being the case, from way back when we learned that the expected value of the Bernoulli was P, and the variance was PQ. So this is our analogous x bars of 0.025, that's from the sample, minus the expected value of our p hat, which happens to be P, over the standard deviation. And the standard deviation is the square root of our sigma squared over n. And here we're living in the world of Bernoulli. Okay, so I guess same game, z sub 0.025, which we know already from a previous lecture is 1.96, times the square root of PQ over n is p hat sub 0.025 minus P. And I just erased it, but it's in your notes. You can see from the picture that p hat sub 0.025 is minus P is equal to our E. Fantastic. So the 95% confidence interval is p hat plus or minus 1.96 times the square root of PQ over N. Now, this formula has a troubling aspect to it. Pause the video, think about what we're trying to compute, and then say why this is troubling. Well, hopefully you said, oh, this is a problem because I don't know P, right? I don't know P, and therefore I don't know Q either. In fact, if I knew P, I wouldn't go through this process. P is the true population proportion. So to solve that problem, what we could do is instead of using P, we could use our best estimate for P. And you guessed it, that would just be P hat and Q hat. So this will be our 95% confidence interval. In general, there's nothing different than what we did last time. So in general, for a 100 times 1 minus alpha percent confidence interval, you'll just use z sub alpha over 2 over here. Right? There's nothing different there. Okay, so let's answer our question. Why don't you give it a shot actually yourselves, pause the video, see if you can put in those values and come to a conclusion as to whether you think the coin is fair based on this data. Okay, so hopefully you said that p hat, well that's just the 4,900 over 10,000. So that's 0.49. Q hat is going to be 1 minus that, or 0.51. So we get 0.49 plus or minus 1.96 times the square root of 0.49 times 0.51 over 10,000. Let's see what this winds up being. We have 0.49 times 0.51 divided by 10,000. All raised to the 0.5 times 1.96. And we get 0.49 plus or minus 0.0098. Ooh, so close. So on the high side, let me write this out as an interval. On the high side, we have 0.499 0.4998. It's almost like I fixed these numbers ahead of time to miss 0.5. Would I ever do that? Maybe. We get 0.4802 on the left. So I want to point something out. Based on this evidence, I would not think that the point is fair, because 0.5 doesn't live in this interval. Let me point out, though, that if I had a higher level of confidence, this z value would have been bigger, and I would have actually captured the 0.5. So that's the thing about statistics. It's not so cut and dry. In fact, there's a great quote from Mark Twain. I think Samuel Clemens was his real name. Statistics don't lie, but liars use statistics. Statistics can potentially be massaged in ways to make your point more, make your point stronger. Statistics are not bad. Statistics are the best tool that we have, but you just need to be aware of what the numbers are, where they're coming from, and this isn't an intro stats class, but if it were, I would really point out the human sides to whatever statistics that you see. Okay, so in this lecture then, what we did is we computed a confidence interval for proportions. And hopefully you're seeing that this is the exact same form and a similar proof involved in coming up with this formula. That's all I have to say. Thanks for listening, and I will see you next time.